So as I go around and give lectures at medical schools, and you do too, people ask us, so why bother teaching doctors about evolution? It doesn't tell you what to do in the clinic tomorrow. What's your answer to whether it's useful for doctors to understand evolutionary biology?
Well, the vulnerability to disease, like all biological phenomenon, have emerged through natural selection and other evolutionary processes. So in order to arrive at a holistic understanding of the problem that you're dealing with as a physician, you need to have evolutionary information. Now, that has not typically been the way we're taught. One way to think about the benefits to physicians is to start with this Tinbergian perspective, to say that typically physicians are taught about mechanistic explanations, proximate explanations of disease. But by pulling the frame out and looking beyond Homo sapiens to other species, and then looking left on the evolutionary timeline, we begin to see an opportunity to understand vulnerability to disease in a much broader context. There are a couple of practical applications of this. One of them is to allow us to look for and find natural animal models of disease resistance. So, natural selection has resulted in an amazing biodiversity that we celebrate and we should be protecting. But that biodiversity is not just in a beautiful range of colorful flowers or amazing insects and fish. It comes in the form of a diverse range of vulnerabilities to disease, vulnerability and resistance. And we have not been paying attention to that. It is actually a precious legacy which is important for us as human beings who care about health and disease.
The doctors who understand that might well think differently about disease.
They might think differently about disease. They might think a lot differently about biodiversity. There was a wonderful study that was done by a pediatric oncologist and some evolutionary biologists that looked at a simple question: why don't big animals like elephants have more cancer? And they went on.
Sounds like Josh Schiffman.
It was Josh Schiffman, it was Carlo Meili, and a group of wonderful people. And they went on to really prove, it needs to be replicated, but to prove that there seems to be a cancer suppression mechanism that these elephants have that allowed them, in a sense, to get to be very, very big without having the burden of cancer. Now, that is one example of a mechanism, a cancer suppression mechanism that's been identified by thinking phylogenetically, that is outside of the animal, outside of Homo sapiens alone. But we can continue to do that. We can begin developing phylogenies of disease vulnerability for atherosclerosis, for congestive heart failure, for breast cancer.
And this is what you're doing now. How many species do you have included? This sounds like a whole life's work project.
Yeah, so Benison Pang, who's a graduate student in ecology and evolutionary biology, and I have spent the last 2 years working on a very, doing systematic reviews of disease vulnerability across the animal kingdom for the top 20 high-impact human diseases, the diseases that the CDC has identified as the most high-impact human diseases. And it's a very time-intense and detailed
So you'd have to figure out, do panda bears get breast cancer? And
so we look in the peer-reviewed literature for reports of, for example, breast cancer in a panda. Remember, breast cancer has been seen all over class Mammalia. The class Mammalia is defined as having breasts, and breast cancer has been seen in, whales and marsupials, and it's pretty much anywhere that there is a breast, there can be breast cancer. So what we are doing is we are using Biosis, Zoological Record, and Medline to really kind of go through tens of thousands of records and create these phylogenetic maps of disease vulnerability. We are taking pre-existing vertebral phylogenies and then superimposing our findings. Our goal is to find gaps. We want to see where to look. We need to know where to look for natural animal models of resistance and vulnerability. There are so many challenges to doing this, but we feel it's a 1.0. It's a first iteration, and an invitation to the rest of the community of wildlife biologists and veterinarians to say, please report your findings. It's relevant not only to your species, but to ours. And importantly, maybe more importantly, it is an invitation to the human medical community to begin expanding the aperture through which it understands health and disease.
So National Institutes of Health has focused on ever more narrow model species for all of its research, 9 species or 10 sometimes. I bet you have really good reasons why you'd like to see that expanded.
There's definite value to animal models. You can study things nano inspection, the kind of, narrow and deep is extremely important and has led to tremendous advances. But equally important and very neglected is sort of the elastic recoil away from that nano inspection, which is a real species spanning approach, which looks for commonalities and differences across species. And recognizing that these diseases that we are so concerned about for ourselves and our families happen spontaneously and have been happening spontaneously, in some cases for hundreds of millions of years, offers us an opportunity to ask new questions and generate novel hypotheses that are not possible without that species-spanning perspective.
And if you're interested in all of this, just go out and buy a copy of Ubiquity. You won't be able to put it down, and you'll get lots more ideas of the kind that Barbara's suggested here. Thanks so much for joining us.
Thank you.